Sure, you can probably explain what a Kubernetes pod is. But what happens when an interviewer hits you with a live 504 gateway timeout and asks you to fix it? Right there, under pressure? That's the moment that separates the junior candidates from the true senior engineers. Because interviewers don't want dictionary definitions. They want to see if you can walk straight into a real production fire and troubleshoot your way out. In this video, we are breaking down 5 real AKS networking scenarios that even seasoned pros struggle with. And I'll show you exactly how to nail every single one. Hey, welcome. If you're getting up for a senior cloud or DevOps interview, you already know this. Kubernetes networking is make or break. But here's the secret. Interviewers aren't looking for textbook answers. They want to see your thought process. Can you stay logical when things get chaotic? Can you stay calm when production is on the line? Today, we are going way beyond the basics of services and ingress. We are diving into 5 advanced failure scenarios that interviewers love to use to test senior candidates. And for each one, I show you the classic junior level mistake, and then walk you step by step through the senior level approach that actually gets you the job.
Alright, first up, the classic. An interviewer says, a user is getting intermittent 504 gateway timeouts on an app. Walk me through how you'd troubleshoot that in UX. The trap, the junior answer. A junior candidate often panics and starts guessing. They'll blurt out, I'd restart the pod, or I'd check the application logs. Now, those aren't totally crazy ideas, but the approach is all wrong. It's unfocused. It assumes the app is guilty and completely ignores the entire network path a request travels just to get there. A504 error is specific. A gateway, like an ingress controller, gave up waiting for an upstream service. The problem could be anywhere along that chain.
A senior engineer thinks like a packet. You start from the outside and trace the request path step by step. My first move is to check the ingress controller logs. This is the gateway in gateway timeout. The logs tell me if the request is arriving and where the controller is trying to send it. An error like upstream timed out is a huge clue. It means the ingress is alive, but it can't get a response from the next hop. So what's the next hop? The service. My next command is kubectl describe as vc service name. I check 2 things. Does the service exist? And does it have endpoints? If the endpoints list is empty, that's a massive red flag. The service has no healthy pods to send traffic to. That usually happens because of failing readiness probes. Next, I move to the pods themselves. I run kubectl describe pod name. I go straight to the events section and check the readiness probe status. A failing probe tells Kubernetes, this pod isn't ready for traffic. Kubernetes then removes it from the service endpoint list. If the probes are passing and the pods look healthy, my next suspect is a network policy. I use kubectl get network policy. In the right namespace, this shows if a policy is blocking traffic. Specifically, whether the ingress controller can reach the application pods on that port. By following this path, ingress, service, endpoints, then pod health, and finally network policies. You show a calm, methodical approach. And you prove that you truly understand the full request flow. Here's the next one. A front-end pod needs to talk to my backend service, but it's failing. When you call http:// my backend service from the pod, you get a could not resolve host error. What's wrong? The common junior response is maybe a typo in the service name, or does the service exist? They'll run kubectl get as vc, see that it's there, and then they're stuck. They treat DNS like a magic box they can't look inside. A senior engineer knows that DNS in Kubernetes is a service itself powered by core DNS. The issue isn't just the name, it's the entire DNS resolution process. The first thing I do inside the failing pod is check etc/resolve.conf. This file tells the pod where to send DNS queries, and it should point to the cluster IP of the kubedns service and include the correct search domains. Next, I check the health of the DNS servers. I look at the core DNS pods in kube system using kubectl get pods -in kubesystem -lk8s app equals kubedns. Are the pods running? Are they stuck in crash loop backoff? I might also run kubectl top pods -in kubesystem to see if core DNS is under CPU or memory pressure. If core DNS looks healthy, maybe the application pod can't reach it. A network policy might be blocking egress to UDP port 53. So I check for any policies in the pod's namespace that could block traffic going to kubesystem. If I still don't have an answer, I debug core DNS directly. You can enable the log plugin in the core DNS config map, then restart the pods. The core DNS logs will now show every DNS query. You'll see whether the lookup for my backend service is reaching the server and what core DNS does with it. This tells you whether the issue is internal service resolution or a misconfigured upstream DNS server. This entire approach shows that service discovery isn't magic. It's a real system you can debug step by step, from the client to the DNS server to the network in between. This one separates the cluster admins from the cluster architects. The interviewer says, you have two pods. Pod A is on node 1 and pod B is on node 2. Pod A can't connect to pod B, but it can connect to other pods on its own node. What's your diagnosis? This is where a junior engineer's knowledge stops. They've checked the pods, they've checked the services. Everything inside Kubernetes looks fine. They might say something vague like, it's a networking issue, because they don't realize the problem isn't in Kubernetes, it's in the underlying Azure network. A senior engineer hears, works on the same node, fails across nodes, and immediately knows this is a cross-node communication problem. This points straight to the CNI plugin and the cloud network underneath it. The first thing I need to know is the networking model. In AKS, is it Kubernetes or Azure CNI? The playbook is different for each. Let's assume Azure CNI, where every pod gets a real IP from the VNet. In that case, the problem is almost always in Azure routing or security rules. My next stop is the Azure route table attached to the AKS subnet. Every node needs routes that tell it how to reach the pod IP ranges on other nodes. If a route is missing or pointing to the wrong place, traffic from node 1 literally doesn't know how to get to pod B on node 2. At the same time, I'm checking the network security groups. The NSG on the AKS subnet has to allow traffic between nodes. There should be a default rule allowing VNet to VNet traffic. If someone added a high priority deny rule, they might be blocking all east-west traffic. To prove it, I'd SSH directly into node 1. From the node, can I ping the IP of node 2? If yes, the nodes can see each other. Now the real test, can I ping the pod IP of pod B from node 1? If that fails, it's almost guaranteed to be a routing or NSG issue. A traceroute from node 1 to pod B's IP will show exactly where the packets are dying. This answer proves you see the big picture, that Kubernetes networking runs on top of real cloud infrastructure, and you know how to debug both layers. Okay, now for a real beast of a scenario. An application is having intermittent failures making outbound calls to external APIs. The errors are random, connection timed out, connection refused. Internal cluster communication is fine. What's happening? This one stumps almost everyone. A junior engineer will get tunnel vision on the application pod. They'll blame the code or the external API. They might restart the pod, which could accidentally fix it for a few minutes, but they have no idea why. They're searching for something that's broken, but the problem is something that's been used up. The moment a senior engineer hears intermittent outbound failures, their brain screams SNAT port exhaustion. SNAT is how pods on a private node share a public IP to talk to the internet. Each node gets a limited number of ports to make those connections. If your app is opening and closing connections like crazy, it can use up every available port. New outbound connections will then fail until a port frees up. My first move isn't kubectl. It's the Azure portal. I go straight to the metrics for the AKS cluster's public load balancer. Azure Monitor has a perfect metric called SNAT connections. If the failed connection count is anything greater than 0, that's your smoking gun. You've confirmed SNAT exhaustion. I also compare used SNAT ports to allocated SNAT ports to see how close to the edge we are. Once confirmed, the solution is twofold. For immediate relief, you can add more public IPs to the load balancer's outbound pool or increase the ports allocated per node. But the long-term fix is about addressing the root cause. This is almost always an application that isn't using connection pooling. I'd work with the devs to fix the code. Architecturally, the best solution is to attach an Azure NAT gateway to the AKS subnet. A NAT gateway provides a massive, dynamically managed pool of ports, making exhaustion nearly impossible. This answer shows you can diagnose subtle, platform-level resource issues, and that you can think tactically for a quick fix and strategically for a permanent solution. Last one, a tricky variation of the first. Your ingress is returning a 503 service unavailable, not a 504 gateway timeout. What's the difference? And how does your troubleshooting change? A junior candidate often lumps 503s and 504s together as the service is down. They'll follow the exact same steps as the 504, looking for a slow app. This completely misses the critical clue in the error code itself. A senior engineer knows a 503 means something very different from a 504. A 504 means the gateway connected but got tired of waiting. A 503 means the gateway tried to connect and found nothing healthy at all. The service is literally unavailable. This completely changes my investigation. I still glance at the ingress controller logs, but this time I'm looking for a message like, "Service does not have any active endpoint." That is the jackpot. My very next command is kubectl get endpoints service name. With a 503, I fully expect to see none under the endpoints column. This confirms the service has 0 ready pods. So, why are there no endpoints? The number one cause is a mismatch between the selector in your service definition and the labels on your pods. I run kubectl describe as VC, service name, and carefully inspect the selector. Then I run kubectl get pods, --show labels to verify the pods actually have those exact labels. A single typo is the most common reason for this outage. If the labels and selectors match perfectly, my next suspect is once again the readiness probe. If all pods are failing their readiness probes, Kubernetes considers none of them ready and empties the endpoint list. I describe the pods and check their logs to figure out why they're not passing their health checks. Is the app crashing on startup? Is the probe hitting the wrong path or the wrong port? By knowing the difference between a 504 and a 503, you show a deeper understanding of HTTP, and you can narrow your search instantly. You're not just following a checklist, you're using the error code as a guide. And there you go, 5 networking scenarios that are way tougher than just defining a Kubernetes object. If you can confidently talk through these problems, you're showing the exact kind of real-world experience that companies are desperate to hire. If this breakdown helped you, do me a solid and hit that like button and subscribe for more deep dives into DevOps and cloud topics. And I want to hear from you. What's the gnarliest networking problem you've ever hit in an interview or in production? Drop it in the comments below. Mastering AKS networking isn't about memorizing commands. It's about building a mental map of how data flows through your system. From the user's browser to the ingress across nodes and out to the internet, every hop is a potential point of failure. When you practice systematic, evidence-based troubleshooting, you can calmly solve anything they throw at you, even when the pressure is on. Thanks for watching.